Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel. Good day, folks. In this fourth episode of our Physics for SSS2, we're going to be dealing with equilibrium of forces. Now, I so much like this topic because most of the time, in several ways in life, we encounter forces, we make use of forces. Even when we talk, we make use of force to talk. Everything we do, we apply force, and that force constitutes work. Now, whether or not this work becomes visible depends on whether those forces are balanced or not. So this is something that is quite subtle, but it's actually the secret of our understanding of how our life and our world functions. So now, by the end of this video, you should be able to understand resultant equilibrium. You should be able to know about how to um, to define equilibrium and properties of a body in equilibrium and so on and so forth. So I implore you to watch this video to the end in order to gain as much as possible. The reason why equilibrium is something that is quite subtle for us to understand in our daily life is because most of the time we don't deal with forces but the magnitude of those forces. So basically, even as a car is moving on the road, there are tremendous forces that are pulling it back. So, but the only reason why it's moving forward is that the forces that are moving the car forward are greater than the forces holding it back. So that is something you should understand that. And because of those forces, at times there's a balance, and at times there's no balance. So when we talk about the force of friction, it is kind of like the balancing force, because naturally in our world, nature wants there to be balance and all the rest. So basically, how do we know when a body is in equilibrium? Now, a body is said to be in equilibrium when, number one, the body acts as a whole. The body as a whole either remains at rest or moves in a straight line with constant speed. That's the first condition. Then the next condition is that the body is either not rotating at all or is rotating at a constant angular velocity. Now that is the second condition for equilibrium of a body. When discussing equilibrium, we often talk about two different types of forces that characterize equilibrium systems or bodies that are in equilibrium. One of those are the resultant force, and that is the single force which, acting alone, will have the same effect in magnitude and direction as two or more forces acting together. Now um, um, uh, we talked about resultant force when we are talking about scalars and vectors. And resultant forces, they are kind of like a compositional forces. They are like the compound forces of different forces acting together. In real life, there are a lot of forces acting on a body, but when these forces are combined together, most of the time what we see is the resultant forces. For example, even the force on a car moving on the road, there are a lot of forces in different directions. The force of the air, the force of the road, force of frictions in different directions. But now when you add this force together, they give you only one single force, which can represent the original forces in magnitude and direction. That's the concept of resultant forces. Then when we understand resultant forces, we can also understand equilibrium forces. But the resultant forces, they are often found by the parallelogram laws of vectors. When we talk about the equilibrium force, it is the equilibrium of two forces that is the single force that will balance all the other forces taken together. It is equal in magnitude but opposite in direction to the resultant force. Now basically, there's a difference between the resultant and equilibrium force, but there's a relationship between them at the same time. The difference between them is that when resultant forces is like a representative of your entire forces, while your equilibrium forces is like an opposition to your entire forces. So resultant is kind of like a representative, equilibrium is kind of like the opposition. It's kind of like the fair match to your forces that can even everything out. So it's kind of like the word and opposite that balances everything out. It's kind of like a work of nature, because nature, as I mentioned earlier, wants balance. Now I hope you understand this concept. Now an example that will help us to understand the equilibrium forces is this. Here we have three forces pointing outward from a point. Now if that point is static, it is obvious that from the laws of equilibrium that satisfies one of the laws, which is the object should not be moving, or it could be in constant velocity motion. Now in this case, if the object is static or moving in constant velocity, anyone, but preferably when it's static, because it's more easier to understand concepts of equilibrium when we deal with static equilibrium. Now basically, when that object is static, any one of these forces can be taken as the equilibrium of the other two forces, because it can balance the others. So equilibrium is all about balance. Now for those three forces that were analyzed in the previous picture, those three forces, they can be represented by a triangle, and that triangle will obey the triangle law of forces, and which principle states that if three forces are in equilibrium, they can be represented in both magnitude and direction by the three sides of a triangle. Now we'll be able to explain this a little bit more further in this video. This is an example which I believe will help us understand the concept of equilibrium even better. Now I told that a mass of 2.0 kg is supported by two cords which make angles of 30 degree and 50 degree with the vertical. So we have to calculate the tension in two cords. Now the problem is illustrated in this figure now. So we are told that the mass is 2 kg, and when we convert that to force, that will be the product of the mass and the acceleration due to gravity, that which is 10. So the product of 2 and 10 is 20 newtons. Now these 20 newtons represent the force that is exerted on that system by the mass of 2 kg. Now when we look at this, it is supported by two cords which makes angle 30 degree and 50 degree with the vertical. So that means when we construct that accordingly, we have this setup. Now in this setup, we can now use this to calculate our answer by using the triangle law of forces. Now here is the solution of the problem, but this is the first solution method, and this is called the graphical method. Now whenever I want to solve this kind of questions with the graphical method, we'll make use of a drawing like this. When we draw things like this, we'll draw them to scale. So that means the length of each of the lines is going to be proportional to the magnitude of the force they represent. So in this case, you can see that this 20 Newton force, the angle of the 20 Newton force with the first tension or string is 30 degree, and with the second is 50, and it is drawn in that order. So where they meet, you can measure the lines of the length of the lines HC and DC to calculate the corresponding forces in the ropes. Now there's an alternative method to solve this question. It's known as the analytic method. When we are solving this question using the analytic method, we don't need to draw our diagrams to scale. All we need to make use of is the sine rule. So we are going to relate the corresponding side with the sine of the corresponding angle. So this is the diagram of how it works. So now for that same question, making use of sine rule, you equate each of the sides and then you look for the missing ones. So when you look for the missing sides, now in this case, always remember that the sides are representing the forces. So whatever you get as your answer will be in newtons. So in this case, we have our tension in the cords as 15.25 newtons and 10.15 newtons respectively. So you can compare your results for the two methods, but most of the time, whenever we are making use of triangular forces in vectors, we'll make use of the graphical, or rather geometric or analytic methods. Now there's another concept that works with equilibrium, and this is the concept of moment of a force. Now I want to talk about the moment of a force. I want you to understand the process of turning a tap open or a faucet. When you turn the tap open, you are making use of a force, and you're applying that force in a particular direction, and there's a distance through which that direction is acting. So that is the way you should understand the moment of a force. Now in this diagram, you can see that when you ride the bicycle, you're applying a force, and that force is rotating around an axis through a distance. And that distance, that's the distance from pedal to the center of that axis, and that is the distance through which the force acts. It's kind of like a perpendicular distance through which the force acts along the center of action. And then when you look at the second way, when you're trying to open a can of drink, you make use of a can opener. Then you are making use of a force, and it's acting through the hand of that can opener. Now that is what constitutes a torque, or what we call a moment of a force. Now, even when we try to open a tap, we make use of anti-clockwise movement, and that forms a couple. Now, in this case, moment of a force is applied in everyday life, and it's very easy for us to understand in that aspect. Based on these demonstrations of moment of a force, we can sufficiently say that the moment of a force about a point or axis C is the turning effect of that force about that point. So it's equal to the product of the force and the perpendicular distance of its line of action from that point. So basically, that means that in a mathematical and equational notation, we will say the moment equals the force times the perpendicular distance of pivot to the line of action of the force. So moment is just like work. So it's just like work in that is basically force times distance. Now let's use diagrams to understand this even better. So since force is in newtons and its distance is in meters, the unit of moment is expressed in Newton meter. It is a vector quantity. So you should know that. Now in this diagram, you see that in the first diagram we have a force acting downwards, and then it has a perpendicular distance from a line of action, or rather from a point of action or axis, which is C. Now the moment of that force is the product of F times D. That's F and D. F times D. Now on the second diagram, we have a force acting in an oblique direction. It's not very vertical. It's neither vertical nor horizontal. So now it has an angle. Now that angle is theta. That theta is to the horizontal, and then it has a perpendicular line of action from the point C or axis C. Now it's still the same thing. All you need to do is you need to resolve that force to a direction that you can easily calculate the moment for. So basically, the moment of that force will be F times D sine theta. So the reason for that D sine theta is because that distance, it is now not along the axis, it is now at an angle to it. So we have to look for the resultant of that distance along the axis. Let's revisit our concept of equilibrium by discussing the conditions for equilibrium for parallel coplanar forces. Now the first condition is that the algebraic sum of the forces acting on the body in any given direction must be 0. So what this means is that the sum of the upward forces must be equal to the sum of the downward forces, or the sum of forces acting in one direction must be equal to the sum of forces acting in an opposite direction. So this is simple enough for you to understand. So you can also use the analogy of a car moving. So there's a force trying to drag the car backwards, and that's the force of friction. And then there's a force trying to move the car forward, and that's the force that is exerted by the engine of the car. Now when the force exerted by the engine of the car exceeds the force exerted by the road that is dragging it back, then the car would move forward. But when you apply the brakes and the force that is acting by the brake pad on the wheels is greater than the force acting by the engine on the wheels, then the car will subsequently move backwards. So that is another way you understand the conditions for equilibrium of forces. Another condition for equilibrium of forces is that the algebraic sum of the moments of all the forces about any point on the body must be 0, or the total clockwise moment of forces about a point must be equal to the total anti-clockwise moments. So this is one simple law of equilibrium. It might not be very straightforward, but because it involves moments, and moments are not readily as understandable as forces to us, but by practice you can be able to understand how moments work. For example, if you've ridden a seesaw when you were younger, you understand that when you move closer to the center of that seesaw, you will kind of be putting yourself at a disadvantage. But when you move further away, you are able to more balance the force of the person that's sitting opposite you. So that is another way that moment works. So the greater your distance, the more the effect of your force. So what we're trying to say here is that the algebraic moment must be equal to the anti-clockwise must be equal to the clockwise moment. So for the condition of equilibrium to be met. Here is an example that can help us understand this concept of equilibrium even better, using the concept of conditions of moment equality. Now you're told that a beam balances on two pivots C and D. A load of 10 Newton hangs at O, 2 meter from support at C. Find the value of the reaction forces at P and Q at C and D. Take the distance as shown. Now this is the diagram here. All you need to do is you are going to balance the moment. So this is an example that is hinged on the condition of equilibrium, which is also hinged on the zero moments about a point. Now you just take a point and then you look for the algebraic sum of the moments in all directions, and then you must equate it to zero for equilibrium to reign. So we'll work that question now. Now continuing from the solution, we have that because it is a light beam, we can ignore its weight. From the first condition of equilibrium, the total upward forces must be equal to the total downward forces. That means P plus Q must be equal to 10 Newton, which is the downward force. Then from the second condition of equilibrium, total clockwise moments must be equal to the total anti-clockwise moments. So that means when we take a random point C, for example, so when we take the clockwise movement about that point C, it must be equal to the total anti-clockwise moment. So the clockwise movement about point C is the 10 Newton force multiplied by the distance, which is 2 meters. That is for the clockwise. Then when we look for the anti-clockwise, that's the multiplication of the Q anti-clockwise times distance, which is 2 plus 6. That's 8Q. That means when we equate everything, we have Q equals 20 over 8, that's 2.5 Newton. Then when we substitute for Q in the first equation, we have P equals 10 minus Q, that's 7.5 Newton. So this is one way. Alternatively, there's another way of doing it. We can take moments about D. So no matter which point you take moments about, you are still going to get the correct answer. So this shows that the equilibrium is also a concept that exists. Another aspect of moments we can talk about is couple. Now, a couple of parallel forces can be so arranged that they can only succeed in causing a body to rotate and not move linearly. For example, when we turn or on a tap, we are applying parallel but opposite directly forces with our fingers, and two such parallel forces which are not in a straight line can constitute a couple if the force are exerted in magnitude but oppositely directed. So in this case, as you can see, when you turn it up, one of your fingers is exerting a force of the couple, while the other is exerting a second force. And the tap will only turn if these two forces are equal and oppositely directed. So that is what is called a couple, and that is used in rotating objects. In simple terms, the moment of a force, or rather the moment of a couple, is the product of one of the forces and the perpendicular distance between the lines of action of the forces. So that is what you need to know, is you need to know the product of one of the forces. You need to know each of the force. So you take one of the force and you multiply it with the perpendicular distance between the line of action of the forces, or if you may, the diameter of the circular path through which they move. So that is how to calculate the moment of a couple. When we discuss equilibrium, we also have to talk about the fact that the weight of forces of acting at different points of the body have a central point of action, and that is where we talk about center of gravity. Now, that center of gravity is that single point through which all its weights will be acting in the body. So now, when we talk about, it's defined as the point through which the line of action of the weight of the body always passes, irrespective of the position of the body. It's also the point at which the entire weight of the body appears to be concentrated. So this center of gravity is the place where the weight is concentrated. Similarly, we can also talk about the center of mass. It is the point where the total mass of the body appears to be concentrated. But for small bodies, like for tiny pieces of paper and all these small bodies, you can assume that the center of mass coincides with the center of gravity. So you can make that assumption. Now, these are common bodies with their centers of gravity. First, we have a uniform rod whose center of gravity is at the midpoint of its middle. And then we also have a uniform circular plate whose center of gravity is at the center. We have a uniform circular ring whose center of gravity is still at the center. We have a uniform rectangular sheet whose center of gravity is at the intersection of its two diagonals. Then we also have a uniform triangular plate whose center of gravity is at its let's call it the auto center, or in center rather. This center of gravity is at the in center, or rather that center that coincides with the bisectors of each of the angles. So basically, that is two-thirds of the length of each of the bisectors. That is the center of gravity of some common. Based on the position and nature of the body, we can talk about three types of stability of equilibrium, and they are stable equilibrium, unstable equilibrium, and neutral equilibrium. So generally, a low center of gravity and a wide base will usually help to put objects in stable equilibrium. So as a cone resting on its base, a racing car with low center of gravity and a wide base, or a ball or sphere in the middle of a bowl are examples of objects with stable equilibrium. So as you can see this theory, this is that cone with its base on the floor is also in stable equilibrium, because when you displace the cone, it will fall back to its its previous state. Then when you have the ball, a ball in the middle of a bowl. So what is stable equilibrium? It's actually the process whereby a body tends to return to its original position when slightly displaced. Next, let's talk about another type of equilibrium, and this is known as the unstable equilibrium. It is defined as a state where a body, when it's slightly displaced, tends to move further away from its original position. So you can see when you have a cone that is resting on its sharp top or its tiny top, then when you displace that cone, it will move further away from its original position. It will topple over. Then, for example, when you have the ball at the top of the sphere, at the top of an inverted ball, and you move it, it will move further away from its position. Now, when we talk about the third example, is called neutral equilibrium. So in this case, as you can guess, you can see that the body is not in any state of equilibrium at all. It is a neutral state, because whenever you displace it, it will move, come to rest in a new position exactly entirely. So what this means, if you move a cylinder resting on its flat flat circular surface, it will move to a new position. So it is not in equilibrium in its previous state. It is just neutral. For example, a base also resting on its circular um, face will also move to a new position of equilibrium. A ball resting on the flat surface will move to a new position of equilibrium. So this is what it's called. Now let's quickly transition to equilibrium of bodies in liquids. Now when you have an object in the water, you will notice that it automatically becomes lighter. So any object in water appears lighter when it's partially or completely immersed. So this experience shows that there's some upward force exerted by the liquid on anything immersed in it. So this upward force is what our Archimedes principle is based upon, and it's called the upthrust. If the true weight of an object in air is given, and then you know the apparent weight in the liquid, then the upthrust is the difference between the true and the apparent weight. So basically, you can see that in this diagram we have the upthrust directing upwards and the weight of the object directing downwards. So the resultant weight is less than the original weight because you subtract the forces. You know that these forces, they are oppositely directed. So the resultant of these forces is gotten by the subtraction of this force. That is one of the addition of forces law. Now basically, the magnitude of the upthrust is given as when an object is totally or partially immersed in a fluid, liquid, or gas, it experiences an upthrust which is equal to the weight of the fluid displaced. Now, this means that whenever you immerse a body, it experiences an upthrust which is equal to the weight of the fluid that is removed from the container. And we can understand this better when we make use of a, um, a tube, a special kind of tube that helps us understand. Now, we can even make use of an experimental verification of Archimedes' principle by suspending an object freely from a spring balance and reading off its weight in water. Now, the object is then lowered into the water and the new reading of the spring balance is noted. So, what this means is you measure the weight of both objects in air and measure the weight in water. Now, you can get the upthrust by the difference between these two weights. So in this example, you can see that in the second diagram, when you immerse the object in water, it displaces some amount of fluid um in another container, and this is basically known as an eureka, yes, as an eureka tube. Another principle that results from our knowledge of Archimedes' principle of thrust and weight of an object is the principle of flotation, which states that an object will float in a fluid, liquid, or gas when the upward when the upthrust exerted upon it by that fluid in which it floats equals the weight of the object. So that means the upthrust exerted on an object must be equal to the weight of that object for it to float. If it is less than the weight, then the object will sink. If the if the weight is greater than the upthrust, then the object will sink. Or if the upthrust is less than the weight, the object will sink. But if the upthrust is greater than the weight, then the object will float. So the upthrust and the weight, they must be equal for the objects to float. So in this case, you can see this diver. So the reason why it floats is that the upthrust exerted on his body is equal to the weight of his body. So that is why he floats. There's a concept which we need to grasp in this part, and that is known as the concept of density. Now, if you've ever heard that of it, density is defined as the mass of an object per unit volume. The instrument used to measure density is known as the hydrometer. So it's used to measure the relative density actually. So relative density is basically meaning the comparative density of objects of liquids with one another. And basically, when you want to measure the relative density of an object, you have to immerse the hydrometer into the fluid. And this is how it works. This is the principle. You place a graph paper and place it inside the length of the test tube. So, and then you hold the test tube in water and carefully add some sand or gravel into the tube with a spatula until the test tube floats upright in the water as shown. Then you read off from the graph sheet the length of the test tube immersed in the water. So you dry the outside of the test tube and float it in a salt solution or brine. Read off the length of the tube immersed in the liquid, and then repeat the experiment with sulfuric acid, kerosene, palm oil, and record the length of the tubes submerged in the liquid. So basically, we are going to calculate the relative density based on the length of the tube immersed, rather submerged in different liquids. And then when you make it up the formula, volume equals mass over density, you can also find that the relation between each of these, and basically the length is inversely proportional to the density. So that means in a fluid that is very dense, the test tube won't immerse very deep, but in a fluid that is not very dense, that is quite light, you see that the test tube is immersed very deeply in that fluid.